Hello, my name is Matthew Harding for SIT 221. So in this unit we've learned about trees, including binary search trees and AVL trees. Today we'll be looking at an application of trees, the Monte Carlo tree search. So in noughts and crosses there are 3 to the power of 9 unique ways for the grid to be populated. To create an AI for noughts and crosses, at most you would need to consider 19,683 alternatives before deciding on the optimal move. This is a pretty trivial task with current computing power. Let's now consider a chess AI. We could brute force the problem as we did before, however it might take a while. Chess has an estimated 3.7 times 10 to the power of 43 possible board states, meaning that all but the most generous of game clocks will have expired before the optimal next move has been determined. The Monte Carlo tree search is used to predict the optimal next step in situations with many unknown variables. It is most used to allow a computer to competitively play chess, checkers, Go, Connect 4, poker, among others. It is best suited to games in which players take turns. The Monte Carlo tree search takes a statistical sampling approach to find the likely optimal move. Now, as it does not evaluate every possible scenario, it's not always accurate. The Monte Carlo tree search can be broken down to 4 main steps: selection, expansion, simulation, and backpropagation. Each step is performed in order and the entire process is looped n times and can be numerically set by the user or based on elapsed computing time. Let's look at the selection step first. So the goal is to select the next node that is to be analyzed. The node must be a leaf. The node could be selected at random, but that would be inefficient, so instead we use a formula to quantify the value of each node. The upper confidence bound formula allows us to quantify the value of any given node. There are 2 terms which determine a node's value: the exploitation and exploration. Now, if a node has a high success rate, the exploitation term will increase, and if a node has fewer simulations than its parent, the exploration term will increase. The exploration parameter is a constant which determines the weighting of each term. If set to 0, the exploration term is ignored. If it's set to near infinity, the exploitation term is ignored. A standard value is root 2, which gives a balance between each. Now, during the selection step, we recursively go down the tree by selecting the child with the highest value until we reach a leaf node. Now, it's important to note that if ni is 0, the value of si will be undefined as we are dividing by 0. In this case, we just set si to the maximum possible value for the data type that you're using, so the maximum value of doubles or floats. Next is the expansion step. So the selected node has its children nodes created and one of them is randomly nominated. Now, if the selected node has never been visited or is a terminal node, as in if the game ends at that node then is not expanded. The simulation step involves performing a run out of the game with random moves, and the simulation ends when the game's over. And finally, backpropagation step is where the result of the simulation is recursively sent up the tree all the way to the root. In most games, players take turns, so wins and losses have to alternate as they move up each node. Now that we've performed a certain number of iterations, we are left with a lot of data and a very big tree, but then how do we select the optimal move? This is simply done by selecting the child node of root with the highest number of visits. It's important to note that the optimal move may not have the best win ratio. So let's look at the Monte Carlo tree search in action. So we've got a simple Connect 4 game here set up and a driver for it to mostly alternate the turns and print it. Now, this is the tree search here, so we can see that we get the root, we get the children of the root, which are the actual moves that we're trying to decide between. We generate them first. Then we start looping until we get the max iteration count here. So we do the selection where we use the root node and we go down the tree until we hit a leaf, and then each time we go down we check the children and check the one with the highest value using that formula we looked at before, the upper confidence bound formula. We then go to expand. Now with expansion, we check to see if the visits are 0 or it's a terminal node. If that's the case, so we're going to return null here. We'll see that in a bit. If that's not the case though, we generate the children of that node and then we pick one of them at random. And we can see here, if we return null, we'll just backpropagate that result and then continue. So if we did expand though, we go to the simulation step here, and we let's go look at it. So we go down here and we keep on looping through the game until we get to a finish, so a draw or win for either player. Then we return that state, so the result of the simulation, and we then backpropagate the state or the result along the expanded node. Let's have a look there. So again, we just go up the tree recursively until we get to root, which will have no parent or null parent. And then once we're done with the iterations, we go here, we select the most visited child, and we send back the result. Now let's see it in action here. So I've got it set up where I'll go first. We've got 10,000 iterations. We're doing root 2 as the exploration factor, and we'll see what happens. So make it a bit bigger. So I've gone here. We can see the visits are quite similar for all the possible moves. This time it's got high visits on move 1. It wants to cut me off, it seems. And we can see the win rates, and that's the value of the upper confidence bound formula there. Now this may seem pretty Connect 4 is a solved game, and if you go first you can always win, but let's up the ante a bit. We'll play Connect 10 on a 20 by 20 board. Now, not quite as easy, and we can see here we're using 70, 90 megabytes, 100 megabytes memory here, so a big tree with a lot of nodes. We're only doing 10,000 total iterations too, so a lot of memory and quite intensive, you can see. Obviously you can bring the iterations down, but it'll make it not as clever. But yeah, that's how it works. My program's code you can find on my GitHub. It's a public repository if you want to have a play around with it. So in my implementation, for each turn we create a new tree. One possible improvement would be to reuse the previous tree. You just need to change which node is referred to as root, and all of the values and visits and all that would still be valid from the previous time, so it would save a lot of time. Wouldn't save any memory though. So should you use the Monte Carlo tree search? Well, it's relatively simple. It doesn't need specific game knowledge beyond just the rules. It does have very high memory usage, as we saw. You need many iterations for it to be accurate though. There's applications for it beyond just games, so in planning, security, patrolling schedules, organic chemistry, and vehicle routing. And that's it. So thanks very much, and hopefully you can beat someone at chess with this. Bye.